Now I'm going to introduce you to one of my favorite rings, the ring of formal power series. For this, fix a field F, any field. It could be the rational numbers, it could be a finite field, it could be the complex numbers, and the ring in question is denoted by F and then double square brackets T, where T is the name of a variable. And this is the set of all symbols of the form. So I emphasize that these are symbols. Even though this looks like the symbol for summation from n equals 0 to infinity, we will never be taking an infinite sum in this lecture. Or for that matter, in this course, this is a course in algebra, we don't take infinite sums. So formally it's really just the set of all sequences a0, a1, a2 and so on in F, but we very suggestively write it using this infinite sum symbol because of the way we will define sum and product in it. So these the operations, the ring operations here are just like the ring operations that we have for actual power series, which you may have seen in complex analysis. So sum and product are defined as follows: summation a n t to the n plus summation b n t to the n is defined to be summation a n plus b n t to the n. And product is defined as follows: a n t to the n summation n goes from 0 to infinity. I need to tell you what the coefficient of t to the n is. What it is sum over all pairs of integers k and l such that k plus l is equal to n ak bl. Okay, so these definitions are motivated from the way in which power series that come up in complex analysis add and multiply. So just to give you a couple of examples, if you take a0 equals 1, a1 equals minus 1, then you get, and an equals 0 for n greater than 1, then you get 1 minus t. Okay, and if you take 1 minus, and then if you take b0 equals b1 equals b2, all of them are equal to 1, then you get summation n goes from 0 to infinity t to the n. And let's multiply these. So if you take 1 minus t times summation n goes from 0 to infinity t to the n, and now you're going to apply this rule here for multiplication, then what you see is that you will just get summation n goes from 0 to infinity, and then you will get k plus l equals n. So but then ak is non-zero only when k is 0 or 1. So so this becomes okay, so first let's write the n equals 0 term out. So the n equals 0 term is just k plus l equals 0, so that is 1 a0 b0 plus, and then you'll get sum n goes from 1 to infinity, and then you will get a0 times bn plus a1 times bn minus 1, because a2 a3 and all are 0. t to the n, but this in turn is always 0 because a0 is equal to 1, a1 is equal to minus 1, bn is always equal to 1, and bn minus 1 is also equal to 1. So this will become 1 minus 1. So the answer you get is 1. Okay, this means the power series for which a0 is 1 and all the remaining terms are 0. So what we have written down is that 1 minus t multiplied by n equals 0 to infinity t raised to n is equal to 1. This power series is just the unit of ft. And so this is the, we can think of this as 1 minus t has an inverse, which is summation n equals 0 to infinity t raised to n. So this is the formula for the geometric series, but we've proved a version of it that doesn't involve any convergence. So this is an identity that holds true in the ring of formal power series, and it can be proved in the ring of formal power series without any reference to the notion of convergence. Another example of an element in the ring of formal power series is summation n goes from 0 to infinity n factorial t to the n. This is a perfectly valid example of an element of the ring of power series, even though if we were working over real numbers, this would not converge for any non-zero value of t. Let's say working over qt or complex numbers. Let's find out what the units in the ring of formal power series are. So we have a field f and we're looking at ft, and we're asking what are the units. So let's just write out the condition for being a unit. So an t to the n goes from 0 to infinity, is a unit if and only if there exists another formal power series n equals 0 to infinity bn t to the n such that this product is equal to 1, which means that on the right hand side we have a formal power series with degree 0 term equal to 1 and all the remaining terms equal to 0. If we write down what this means in terms of multiplication that we had just defined in the ring, this means that we have to compare the coefficient of t to the power 0, the constant term, and what we get is a0 b0 is equal to 1. Then it also means that a0 b1 plus a1 b0 is equal to 0. a0 b2, comparing this is the coefficient of t on the left hand side, 0 is the coefficient of t on the right hand side, and comparing the coefficient of t squared, we get a1 b1 plus a2 b0 equals 0. And generally what we get is, comparing the coefficient of t raised to n on both sides, we get a0 bn plus a1 bn minus 1 plus dot dot dot, and this goes all the way to an minus 1 b1 plus an b0, and this also needs to be 0. So if this element summation an t to the n is a unit, then obviously we need that a0 is not equal to 0, and then we can solve for b0. b0 is a0 inverse. Okay, now suppose we've solved for b0, then we can solve for b1 using the next equation. What we get is b1 is equal to minus a1 b0 into a0 inverse. And we've already solved for B0, which is A0 inverse. And now we can solve for B2. We get B2 is equal to minus A1 B1 minus A2 B0 times A0 inverse. And these can be calculated no matter what the values of A1, A2 and so on are. We already know what B1 is by the previous equation, and so recursively we can compute Bn to be minus A1 Bn minus 1 minus A2 Bn minus 2 minus all the way down to minus An B0, and then that multiplied by A0 inverse. So what this tells us is that if summation a n t to the n is a unit, then A0 must be non-zero, and moreover, if A0 is non-zero, this gives us an algorithm to compute the multiplicative inverse of summation a n t to the n. So what we have shown is that summation a n t to the n goes from 0 to infinity, is a unit if and only if A0 is not equal to 0. What are the ideals in the ring of formal power series? To understand this, it's useful to have the notion of the valuation of an element in F. So for any F in Ft, you can write F is of the form n goes from 0 to infinity, a n t to the n. Define the valuation of F, denoted Vf, as the minimum value of m greater than or equal to 0 such that am is not equal to 0. So for example, if f is a unit, then we know that a0 is not equal to 0. So then the valuation of a unit is 0. And in fact, an element is a unit if and only if its valuation is 0. Now let's see what principal ideals in the formal power series look like. I claim that the ideal generated by F is the set of all G in Ft such that valuation of G is greater than or equal to valuation of F. So suppose we have an element F, then we know that we can write F as summation n greater than or equal to valuation of F. So we can write it as a valuation of F t to the valuation of F plus a valuation of F plus 1 t to the valuation of F plus 1 plus dot dot dot, where this first coefficient here is non-zero. That's just the definition of valuation of F. So I can write this as t to the power valuation of F times a valuation of F plus a valuation of F plus 1t plus and so on. Now this thing in parentheses here, this expression is a unit because it is a formal power series whose constant term is non-zero. For some unit u. So what we have is that the ideal generated by F is the same as the ideal generated by t raised to Vf, because F differs from t raised to Vf by multiplication by a unit. But what is the ideal generated by t raised to Vf? It is all multiples of t raised to Vf. And so this is equal to just t raised to Vf times G, where G is any element of Ft. But this is of course just the same as G in Ft, such that valuation of g is greater than or equal to valuation of f. In fact, the valuation of t raised to vf times g is the valuation of f plus the valuation of g, which can be anything greater than or equal to 0. Because if you're looking for the first non-zero term of t raised to vf times g, it is the first non-zero term of g, wherever the first non-zero term of g occurs, shifted to the right by v to the f. So there you go. So the principal ideals are just determined by the valuations of elements. Okay. So now I claim that every ideal of ft is of this form. So suppose I in ft is an ideal. I want to say that I is of the form t to the power m for some integer m. So how do I find that integer m? Let m be the minimum of the valuations of all the elements of I. Then of course I has an element with valuation m. So then there exists f belongs to I such that valuation of f is equal to m. Now the ideal generated by f is going to be contained in I, but the ideal generated by f is t to the power m. So the ideal generated by t to the power m is contained in I. On the other hand, I want to claim that I is contained in the ideal generated by t to the m. But recall, this consists of all elements g in ft such that the valuation of g is greater than or equal to m. Okay, so to show the converse, I is contained in t to the m. We just need to show that if something is not in the ideal contained in t to the m, then that means that valuation of f is strictly less than m. But by definition of m, f is not in I. Right? Remember how we defined m? We defined m to be the smallest possible valuation of the elements of the ideal I. So what we have concluded is I is equal to the ideal generated by t to the m. And there's one more ideal, namely the ideal 0. So ideals of ft are 0 or the ideal generated by t to the m, where m is greater than or equal to 0. So this is the set of ideals of ft. And one interesting point about these ideals is that each one they form so the smallest ideal is 0, and the largest ideal on the other hand is ft itself, which is t to the 0, and this ideal contains the ideal t to the power 1, this contains the ideal t to the power 2, this contains, and so on, and they all contain the ideal 0. And you could ask what is t to the I plus t to the j? Well, you can think about it. It's t to the minimum of ij. And what is t to the I intersect t to the j? It's t to the maximum